Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today's topic of our discussion is tracking. So, let us understand what is meant by object tracking. It is an estimation of a trajectory of an object in the image plane as it moves. So, the input of this particular task would be a temporal sequence of images or a video, and this could be considered under different contexts. Like we can consider the tracking problem as a single object tracking or multiple object tracking, or it could be a trajectory in two-dimensional space like in the image space, or it could be three-dimensional trajectory where you consider the 3D world coordinate system where a three-dimensional object is moving. It could be a tracking of points or it could be tracking of a body. The motion could be rigid body motion, it could be deformable body motion for which the tracking algorithm has to be designed, or it could be a processing which can be done offline, which means not exactly the real time or semi real time computation, but no, you have the video and then you are trying to find out the trajectory of an object within the video, which is an offline computation. On the other hand, it could be an online tracking, which means you are capturing the video sequences and also tracking the objects. Some of the scenarios which we are depicting here that you can see here, for example, you see the leftmost and topmost image where cars are moving on two lanes. One is incoming car, another one is outgoing car. So there you can see it's a case of multiple object tracking under these traffic conditions. If you see the rightmost image where once again these cars are moving, but the vehicles movement has several kind of components, and there are rotations, there are even there are accidents kind of scenario which is considered here. And the third one, which is the bottommost and the leftmost and bottommost one, where several persons are moving and they are moving like their body is tracked like a set of points. So, let me discuss about one particular concept related to tracking of objects, that is of optical flow. An optical flow in a video sequence, it is a distribution of apparent velocities of movement of brightness pattern in an image in each frame. So, in this case, we consider that the brightness value of pixels, those remain constant along the motion of the object points. So, the pixels representing a point, its brightness value remains constant in say 2 consecutive frames and so on. So, from there that can give us a clue to the projected velocity field of that point. So, let us understand that how this information can be, how this constraint can be mathematically exploited. So, let me consider once again the image. I represent it as a spatial distribution of intensity values. So, in this case, as you can see that at the tth frame, that means at time instance t, the intensity value at that point is considered as we are representing as a function of a three-dimensional variables like space x and y and also the temporal domain time. So, when we consider the pixel value at a point for the next time instance at a interval of say delta t, and also due to the motion, if I consider that pixel has been moved to the point say delta x and delta y, since we are considering this function is a smooth function in a 3 dimension, so we can perform a Taylor series expansion in terms of the functional value at x, y, t, and then we take the first order derivatives approximation. So this is the change along x, so di dx, or if I strictly write, it would be partial derivative with respect to x, and then you multiply with delta x. So this could be written in this form, and similarly I am following the notations for my convenience. I have used this notation dy dy into delta y and di dt into delta t. These are all partial derivatives. Also there will be higher order terms like second order derivatives, third order derivative terms, but we know that those values, they become smaller and smaller, and sometimes we ignore them. So we will assume them for our convenience, simplicity. We assume that this expansion is still this first order derivative term. So since these two remains the same, so this part we can see that this part we consider those changes there should be equal to 0, and where we approximate with only first order terms. So from this constraint itself we can express express this relationship into this form of equation. So this is di dx, or partial derivative of intensity with respect to x. This one is partial derivative of intensity with respect to y, etc. So I can rewrite this equation by considering the derivative or differential by taking delta t in the denominator. So now this is the approximation of the velocity in the projected space. So along x direction, so we write it vx, whereas you note a little bit of notational ambiguity here. Here ix refer to del partial derivative with respect to x, but vx is the x component and vy is the y component of the velocity field. So this is the notational ambiguity. I request you to bear with me. So this is the equation. As you understand, it here basically means partial derivative with respect to t, and iy is partial derivative with respect to y. So this is the equation, and in a short form, in fact, we can write it in a nice short form. Let me just clean the thing. So as I said that delta x delta t is vx, delta y and di dy is iy, of course. So this one is actually vy, delta y delta t. So as you can see that it is conveniently represented in shorter form as grad of I in dot product of grad of I vector and the velocity vector, which should be a scalar component, which is the change of the intensity values along the temporal, and it is a change in the opposite direction, that means in a negative direction of it. So which means that say grad of I can be written as a vector, say delta I delta x and delta I delta y. I can write it also as a column vector, but since I am using dot product, so and v here is the velocity field where I am writing it as vx and vy. So if I write these two dot product, so this is the same what it is, and then it comes at the right hand side, so that is equal to minus it, means this is equal to minus delta I delta t. So with this equation we can what we see here actually that this gives us a single equation for a particular point. So but there are two unknowns, vx and vy. So this as such the number of unknown is more than this equation, so it is an underdetermined set of equations. So we require additional information to solve for vx and vy. So one thing we could do that we may consider around that point, we may consider more points. So let us take another point. So this point and this point, if I assume both of them are having the same velocity of movement, that is for a rigid body motion and for an object motion, it is quite a pragmatic assumption. So in that case, you get two equations and then you can solve them. So with minimum 2 points constraint observations, you can solve, because all these things are computable from the data, from the sequences. All these component, like the derivative with respect to x, derivative with respect to y, then derivative with respect to time at any point, all these things are computable. So if I have two equations, I can solve it. Or what we can do, we can consider a for making it more robust, because there could be noise, it could not be exactly 0. Rather, we can consider an optimization problem where we would both try to minimize error due to this. That means this should be small. So if there is any value, that is the error. So we can take simply the square of this value, and we consider the velocity profile should be smooth. So the smoothness criteria in this kind of regularization task, we call them regularization. If we apply that, that may be also used for solving this. And that is another kind of constraint we are trying to put here. So smoothness means we would like to minimize the Laplacian of the variables Vx and Vy. Both they should be Laplacian should be small, or we can also consider the square of the norm. So actually this is a magnitude, so it is not a vector, it is a scalar. Laplacian of this norm should be small, or square of the magnitude of the gradient value. Any of the criteria you can consider. So let us try to see that how we can use these constraints to solve this problem. In fact, this is the very first technique on optical flow which has been proposed by Horn and Schunk. I will be considering just discussing on that particular term. So as I mentioned, you can minimize an objective function which will be considering as the error term, because all of them we try to make it 0. This should be 0, this should be quite small, near about 0. So these two, a linear combination of these two will define an error. Or you can also you note this Laplacian definition here. These are definition of the Laplacian. So all these things are partial derivative, you should note here. And this another function could be this. So any one of these function you can take, but then you can use the respective differential calculus, theory of differential calculus, and you can solve this problem. So here this k is a constant. So this k is a constant. Okay, and we from dE by dVx equal to 0. So we solve these two equations, and we can show that effectively, if I use E2 and if I apply these constraints, these equations, if I take the derivatives and form these equations, those equations will be formed in this fashion. So you get two equations. You can note that. But one of the things you should note that though you get two equations, their neighborhood information is required, because this derivative Laplacian, you require neighborhood information. So it is not really independent in that sense, because you require neighborhood velocity profile. So what we try to make this problem as solving a set of linear equations where each point has its velocity profiles, and try to attain this kind of try to minimize this objective function. So this is how this computation is designed, and one of the approximations what we do, that Laplacian of a variable v can be approximated into this form, and in the 3 dimensions usually in 2 dimension, because this variable is a distribution in a 2-dimensional space, like the x component of the velocity profile. So that is a variable. So this is you should know this is a scalar component. So if I take the if I take the average and subtract it, this is actually the discrete form of approximation of the Laplacian of a variable in a space. in general, and this constant c is taken as 3 in 2 dimension. So if I replace all of them in those two equations, then I can form these equations in this form. You can see that now these are the equations where actually as you can see that this representation means it is the average of, this is actually average of the x component of the velocity, and this is the average of y component of the velocity. So these are the two equations you need to solve, but as I mentioned, average means you require the neighboring information, so they are not really independent, and you for n points you can get 2n simultaneous equations, and we try to solve them using an iterative method by which we update it and we try to see that objective function gets minimized. So when the iteration converges, there we stop. So this is the method of optical flow by which you can compute the velocity profile of the points in a particular space. So if I get an image, for example, if I have two frames here, so this is an object which is moved here, so it models a translatory motion. So for each point, we consider sum of the velocity profiles we will get. See, if there is another object and which is moving here, so we will get another velocity profile here, and with certain tolerance, with certain noise distribution. So this is the kind of flow distributions that you can get from two consecutive images, and you go on computing these things. So this is what is the computation of optical flow, and there are certain advantages and disadvantages with respect to the solution of an object tracking problem, as you understand. So one of the advantages is that we have not assumed any kind of shape or motion. That means it is very generic in approach, and the object's appearance is not modeled at all. And later on we will see that that is one of the key information that can be utilized for the tracking of objects in the higher level of processing. And then so it is also applicable for rigid body or deformable motion. So very fundamental computations in that sense to understand the motion of the different particles in a three-dimensional world on the projected space. But there are some of the disadvantages as well, as you understand that it computes for every pixel but does not model the whole body motion. So which is not considered, that becomes again another kind of bottleneck because the object motion is not really modeled. Then aggregation to be done as a post-processing. So later on we need post-processing, of course. So this does not give directly the motion of the objects, and which may be non-trivial. And it is quite computationally intensive because you are doing it for every pixels, almost every pixels. So that is what you do. That's why it is. This is also another disadvantage. And if there is a noise, it is susceptible to noise. There is another kind of approach which is called Canade-Lucas-Tomasi tracker approach. Here also we follow similar principle of optical flow, but that means we consider that intensity remains constant in the direction of movement. So you consider particularly this scenario. As you can see that this object is moved from this location to this location in the next frame. So this is the direction of movement. So D denotes the direction of movement. So that's the vector. So along that direction, the object is moving, which means the respective intensity values due to this displacement, they should again remain constant. So I should say that Jx equals the intensity at x in this case should be related to the Ix minus t. So in the backward direction. So any point here is related to here. So this is what is, if it is x, this is x minus t. Suppose this is x minus t. So you have Jx equals Ix minus t, and once again you can write using that kind of Taylor expansion that Ix is grad of I dot t, So there, if you ignore the higher terms, so we can write the difference of intensity values between Jx and Ix is actually grad of I dot d. So that is what, no, it is same as the, temporal derivatives, proportional to the temporal derivatives, and this is the spatial derivatives along that, motion, spatial derivatives along the direction of motion. So it is almost giving the same equation. So you have to minimize it. So what you require to minimize at a neighborhood of x, so you have to find out that d which minimizes this operation. So you search in the neighborhood of x and respective jx, so which will give you this kind of minimizations. Now this minimization problem, it could be weighted. You can give more weight to the central pixel and lesser weight at these peripheries, and so this is how you can do it. Once again, if I apply the derivative of E with respect to derivative of D, these expressions can be expressed as you can see, this is also this is W prime H minus delta I D into delta I equals 0. So this W prime is a normalized, actually this is a normalized weight because it is divided by Wx, the sum of Wx. So H is Ix minus Jx, so this is H. So that is what you are getting, H minus, so just simple derivative. So this derivation itself will give you H minus delta I dot D into delta I. So that is what you are getting. So from there you can compute D. Using this equation, you can compute D. So delta I dot D also can be written as delta I transpose D in the matrix notation, and this can be this equation can be written in this form: W prime, which is the normalized weight, is equal to H into delta I and then delta I into delta I transpose D. So, and as you know that this is column vector. So finally D could be computed as you see that if I take it this side, so this is the inverse of this, and so this matrix, so this summation is still there, and this is along neighborhood. So this is actually here. So you understand that this is a function of x, this weight is a function of x, what is being considered here. Even this matrix, these are also function of x. This x is a pixel value, and this is a 2 cross 2 matrix. So one of the issues would be for KLT tracker, because you want some kind of rigid body motion, the concept of optical flow from the using the same concept, but here we are trying to model some kind of rigid body motion. So we would like to see only those points where the motions are more perceptible, that means changes are more perceptible. So, and where the corners like we have seen in ordinary feature detection also, corners are more suitable for detecting those changes, perceptible changes. So a similar principle to Harris operator could be used to identify the corners, and only you consider the motions along those corners. So from there the displacements are computed. So eigenvalue of this at x should be high. So it is the same quantity what we have earlier also we have used for Harris corner detections, where we consider the eigenvalues of this. So if I make the respective I should say singular value decomposition or eigen analysis, the eigenvalues should be they denote actually the kind of changes at direction, minimum and maximum changes, as you have remembered. So naturally the smaller eigenvalue should be significantly high, and that is why we can apply that method, that minimum eigenvalue to be greater than a threshold, and only at those points this D is estimated, and then use that estimate once again to apply for understanding the motion of the object. So now let us consider the object tracking problem, overall object tracking problem. So we have just given typical examples of computing the motion at the pixel points, and even some kind of similar modeling over the movement of a body, though we are computing at a pixel point there. But in the scenarios where actually a particular object is moving, so we require to have certain kind of representation of that object, and then identify the presence of the object in subsequent frames. So that's why there are two things for representations. One is that you can perform certain feature extraction, and then you represent that object. So target is the respective. So target is the respective object what we are considering, which is to be tracked. So this representation with respect to this feature is important, and then what you do, you consider its presence in the next subsequent frame, which is called localization, and you perform certain kind of management. That means some kind of control of over the estimation process, localization process, so that the object remains in the window of your search, window of your visibility, if I say when you are processing it. So your objective is that, and you should know that when the object exited from the screen, from the video frames itself. Anyway, so those are the issues on the managing that, and using them actually you are generating the trajectory state. So trajectory state is nothing but the information about the trajectory, the location of the object and its respective velocity and acceleration, etc., those profiles. And so those are the results, metadata are those results, so related to the state information. So there are different approaches for computing this. So like it could be a generative tracker, where first you establish the appearance model for the target, and then you search the region similar to the target object in a continuous sequence. So the learning appearance model is critical in this case, and there are various techniques for doing that, like you can have subspace learning, sparse representation, spatiotemporal motion energy, Boolean map, different techniques that you can get in the literature. Another approach for tracking is a discriminative tracking approach. So in the discriminative approach, what we do that we consider the problem as a binary classification problem, which means that it is required to distinguish the target from the background. So if I consider a particular candidate block or candidate zone or window in my search, then our classifier will tell whether that itself is the background or whether that is a part of the target. So in that way you localize the object. So correlation filter based tracker is an example of this kind of discriminative tracker, because you can classify, you can design, you can train a classifier based on the input labeled data of tracking. So you can basically learn a filter, and that filter is used for doing this job. There could be collaborative tracker, where it take advantage of both generative and discriminative approaches, and there are deep learning based trackers where it combines the deep features with traditional tracking algorithms. It has end-to-end learning of a deep neural network for tracking. So there are two approaches there. One is that you extract features using deep learning model, and then you go for traditional tracking algorithm. The other one could be design a model where end-to-end learning takes place. That means given the sequence, it will also predict, and given the sequence and also the description of an object and its say first position, it will estimate the subsequent positions and other pose of the object. So when you talk about generative tracker, the critical point is that the appearance model, and then we search the presence of that object using that model. So there are different ways this appearance model could be described. It could be described by points, it could be described by kernels, silhouettes, or moment invariants. So these are different shape representation or abstract feature representation, algebraic form of feature representation. Not algebraic form, it's a feature representation. If you have distribution, and also you can use certain distribution based descriptor for this model, like histogram of pixel intensity, histogram of gradients. You can use shift descriptors, where once again it is basically histogram of orientations around a neighborhood, or you can there is another technique called GLOH, so that also you can consider. Then this descriptor could be differential descriptor, where the steerable filters or Gaussian derivatives are used, or there are several binary descriptors. We have discussed about this, some of them like brisk, Warby, brisk, brief and Warby we have discussed. It could be spatial frequency based descriptor, like use of Gabor or Haar wavelet responses, or surf feature vector. So these are certain examples of the appearance, how to build up the appearance model of a target. Now when you are searching a target using this feature descriptor, which we can in general consider as a feature vector for description. So what we do, we use a similarity measure in searching the object location in the next frame. So normalized correlation coefficient is one such popular similarity measure. What it considers, that if you consider a particular region around the pixel x in the tth frame, and then you consider the same size of region at the location of x plus u in the next frame, then you define the correlation coefficients, normalized correlation coefficients between these two by making correspondences of the respective image points of the block. As say suppose this is x site position and this is the image IT, and suppose you have another position, say which is position is x plus u, and say this position is x. So you have a block around it, similarly the blocks of same size, and it has, you make a correspondence between these pixels in its respective locations. Now using these correspondences, you can compute this normalized correlation coefficient. That means, as you can see, that you are taking product of this and this by this expression. Similarly, by taking the sum of itx square and sum of this. So, it is similar to the correlation coefficient where we assume actually 0 mean for a random variable. But anyway, so this normalized correlation coefficient can be used for identifying the object location in the next frame. So, wherever it is high or this peak, you consider that is the position where this object location occurs. You see that this u is the velocity, and as I mentioned, it can be defined also in a feature space. We have used in terms of intensity values, but in a feature space you can also define it. So, that was kind of one of the type of generative tracking approach where you use a model, appearance model, and compute the correlation between the blocks of two subsequent frames, and from there you try to establish the presence of an object. The other approach, which is called Bayesian tracking approach, here what we have that we consider in this case we have a state space representation of an object at every time instance, and transitions from one state to another state takes place due to the movement and as you progress along time. So, xk is that state. Similarly, at k plus 1 we denoted it by xk plus 1, and they are governed, these state changes governed by a motion dynamics, which is expressed by a function fk, and this vk minus 1, as you can see here, this is a noise, IID noise, and what you are doing, an object is moving. So, when it is moving, it is going from one state to another state, and there is a measurement of that object. So, this measurement could be the respective image locations and also the orientations, etc., or I should say optical flows along those in these two locations. So, these are certain measurements. So, you measure the optical flow, you measure the location. Now, let us represent whatever may be the measurement that is you observe. So, let us represent it by the variable z, and for kth instance we use it zk. And similarly, there is a relationship between the object's presence at kth instance with this measurement, and this is expressed by this function from hk. So, you have two functions here. One function estimates, or one function expresses the object's position or rather object state in the next instance, and the other function, given the objects at that state, it provides the measurement of that object. So, what you need to do in this Bayesian tracking approach, that we have the series of measurements. That means we know the location of certain windows which is related to that object that we consider, and locations and velocities in the projected space, etc. So, let me just represent it using simple variable z. So, we have this observation measurements from its first frame of the video sequence to the last one at the kth instant. So, you have all these measurements. So, that sequence in a shorter form, I am representing as Z1 : key. So given that measurement, so that is the Bayesian tracking problem, you have to compute the state of the object at kth instance, which is denoted by xk. And we should assume also that initial state is given to us, and also the probability of that initial state also is given. So here for Bayesian tracking, we need to compute the posterior of the state, posterior probability of the state at kth instance given the measurements till kth instance, given all the measurements till kth instance, which is expressed by this probability of xk given z1 to k. Now the method by which you can solve it, you recursively you can compute these probabilities. So which means that if I know the probability of k minus 1th instance of a state, then given the measurements till k minus 1th frame, so from there you can compute this one by applying Bayes rule. So this is what is your Bayesian tracking. So we perform this computation by some kind of recursive process. Now one of the theorem in this regard is very relevant, that since you know the measurement from 1 to k minus 1 and then you are going to do the kth measurement at the kth instance. So what is the probability of the object, state of the object at kth instance given the measurement from 1 to k minus 1. So in this case what we do, that you consider that what is the probability of any position which I am denoting as by xk minus 1 given z1 to k minus 1. So what is the probability of that, and then given that position what is the probability of xk, which I am expressing in this form, and consider all sorts of possible states at k minus 1th instant. Which means that suppose you have an object, it is moving, this object is moving and you are taking measurements of this object in an image. And this is a measurement, so I am writing it as z1, z2, and this is what is zk minus 1. So now if this, and this is suppose this is a state xk minus 1. Now when this object moves to when the object is moves to kth instance, which is xk. So what we consider, that what is the probability of xk given xk minus 1. So we are using the first order Markovian principle, because the governing equation, it says that xk position is function of only xk minus 1 and also some noise that we have seen. So what is this probability of this one, and what is the probability of that we already know, xk minus 1 given z1 to k minus 1. So this multiplied by this will give one probability. Now this could come several, say there is always uncertainty associated with xk minus 1 in the probabilistic interpretation. So this position is not the precise position in the probabilistic sense, it could be here, it could be here, it could be here. So for each transition, what is this probability, and then again for each one, what is the probability for all this measurement. So these are the two factors that you see, and you are integrating over the xk minus 1, all possible space. So that is the expression for Kolmogorov equation, and this is something like prediction. So you are predicting the xk from the past k minus 1 observation, or also you are predicting xk from xk minus 1, in other sense you can say, right. What you do here, you consider as I mentioned, that due to the first order Markovian principle, you are writing here in this form, and that is how this is simplified, this gets simplified. So I can write the whole thing as in this form, as you can see this is, and this is the prediction from, as I mentioned, from the measurements. Now you apply the Bayesian rule, because if I know the probability of xk z1 to k minus 1, and also then I need to find out that how this gets improved with the measurement zk. So which means that if I consider the actual problem, that probability of xk given all the measurements from z from 1 to k, so I consider what is the probability using Bayesian rule of zk given xk, and then probability of xk given zk, and that means z1 to k, z1 to k here actually, yes, what is the probability of z1 to k, and then probability of zk given measurement given this. So this is a Bayesian Bayesian rule. If I apply, this is what you will get, and where you get this expansion. So you consider all possible states once again, providing the measurements of zk. So this is an update equation. So this measurement is an update. So once you estimate xk from the past k minus 1 observation, then you update the value with the present zk operation. So this is what is the recursive Bayesian tracking problem. So a special case of this recursive Bayesian tracking approach is Kalman filtering, where we assume that posterior density at every time step is a Gaussian density function. So we consider the probability of xk minus 1 given all the measurements from 1 to k minus 1 is Gaussian. Similarly, probability of, so it is a theorem that if it is Gaussian, then you can show that probability of the kth state xk given this past 1 to k minus 1 is also Gaussian, which was the prediction state. So this is the prediction. So since xk is related to this linear system, so when it is a linear functional relationships, then only it is Gaussian. When it is a linear functional relationship, then only Gaussian. That can be shown. Now the linear relationships are expressed in this fashion, as you can see, fk into a xk minus 1 plus vk minus 1, which is a noise with 0 mean, and q k minus 1 is its corresponding covariance matrix, and the measurement, that is also a linear measurement with respect to the state xk, and there is also an error noise associated with this measurement uk. So this is the model. So given the movement, you can from the past position, you can get the next positions using applying this model, and also the measurement from that position you can get the measurement. So the posterior densities with respect, these are the components xk minus 1 given z1 to k minus 1. So you note that here this is critical, right? This one is critical and this one. So these two, that you are predicting, you are finding out the probability of the state at k minus 1 given the observation still k minus 1. So, just to denote these variations, we use the density functions, the parameters, we denote them. We use this kind of notations instead of comma, semicolon, we use this just as if given k minus 1, you are estimating also k minus 1 for state. So, this is a mean and this is a covariance matrix. Similarly, for this distribution, when it is kth state, you consider this is the mean. So, these two means are different, as you see that these subscripts are different. So, they denote this distribution, where qualifying thing is that it is for xk from the observation this. And the third one is that you are observing the kth state with all the measurements from 1 to k. So, then the Gaussian distribution has this parameter which is denoted by this k by k from k and pk, k from k. So, one of the things you should note that state measurements and equations, state and measurement equations are time varying, which means this fk and hk, they are time varying, they are dependent on k. So, it is a very general situation. So, the problem of Kalman filtering is that given the functional relationships, density functions and the measurements, that means observation till kth instant, you have these relationships, then you have to compute the xk from the measurements, all the measurements. So, estimate parameters of these density functions and then you can perform this. So, when you are estimating this parameter for prediction, you are applying the same linear model. So, since this was the mean value, if you note that this is the mean value of the probability of the state. So, mean value of the probabilistic sense, there is a mean positions in the mean state of the previous state value of the k minus 1th instance. So, you consider this. Similarly, the variances, we know that variances could be modified by the linear operations in this fashion, in that quadratic fashion. And then of course, since there is a noise associated with it, that would be added. So, these are the two predictions of the new position. So, you have the k minus 1th position, you go to the kth position. If this was mk minus 1, so you apply fk operation, you get fk into mk minus 1 would be the new position. Similarly, if it is associated with some pk minus 1, this will be also modified by this term. So, this is what is the prediction, but after that you observe, you also taken the observation. Suppose this is your observation of the object. Suppose this is your observation. So, what is the new prediction? What is the update of this prediction? So, when you do update, you perform this. That means you consider this position now. So, this is what you have computed. This plus you see the difference between your observation and if I apply the relationships of the estimated position and the measurement, then this difference need to be compensated with this update. So, there is a gain factor which is called Kalman gain and the dimensionality has to match. So, this Kalman gain is multiplied with the difference to update this position. Not only that, even the variance is also updated accordingly. So, this can be mathematically proved and shown that how this these are derived using that Bayesian recursive approach. The way we have computed, we can come to these expressions. So, this is what is now Kalman filtering. That is the recursive solution for Kalman filtering, and this is known as Kalman gain, as I mentioned in this case. And to complete the whole story, actually once you update, then that you have to, so how do you compute this Kalman gain? That is the question. So the Kalman gain is computed in this fashion. So you know this particular, this is given. This is already known to you. So this is computed from the measurement. So this is the covariance matrix due to the measurements. This is the covariance matrix due to the measurement, and then Kalman gain is given by this expression. Once again, this is something from the theoretical analysis you get these expressions, but this is how the Kalman gain is computed. So with this, let me stop here today, and we will continue this discussion in the next lecture. Thank you very much for your patience and attention.